All right, so here's where we were last time. We were talking about doing integrals using polar coordinates change of coordinates functions as change of variables functions, right? It's kind of a creative idea, frankly. We thought of polar coordinates change of coordinates function as just kind of a thing you do to turn these coordinates into those coordinates, but you can use it also for pullbacks, right? So we saw this example where, of course, the big step, in some sense, the sort of mathematically significant step is rewriting dx dy as rd theta. Don't forget that r. Again, that's the big point. It's really the biggest point in this process. And then, of course, there's just plain old basic plugging in stuff, and then finding what the bounds are that correspond to the pullback domain. And as a result, I end up with an integral that's so much easier to compute than the alternative, doing it sort of brute force as it was given to me. Of course, gets square roots involved, and if you crank this out directly, you're going to find that it is doable, right? But it's a lot of ugly. So much better to do it this way. And then we made the realization, and I didn't phrase it this way, but I like the following phrasing. You can think of it as pulling back the domain, or you could instead think of it as pushing forward the slices. Right? Excuse me. So this theta slice right here, I can think of what it looks like in r theta space, or how about this? I could just think of what it looks like in xy space. Right? That's what that slice looks like if you push it forward into xy space. So just think of it over there. So revisiting then the exact same example, notice I have here my r theta plane and my pullback domain and you could think of the slicing process there, but notice I've got that scratched out. Right? Visible for comparison purposes, but the point is, instead of thinking all that pullback nonsense, think of what those slices look like over here, and it's pretty easy to persuade yourself that we're starting at theta equals 0, and we're ending at theta equals pi over 2, etc. Right? So notice then I don't have to redraw my picture. I don't have to figure out what does the pullback domain look like. Which is kind of it's a nice little streamlining. And that's where we left it last time. Okay, so moving along, more of the same. And by the way, what we're going to find today is mostly the ideas that I've just talked about. We're going to do a bunch of examples. And then we're going to do the exact same, morally same thing in the other coordinate systems. It's going to be a lot of the same ideas. Yeah.
Can R be negative?
No. So this is, I guess technically you kind of could, but why would you ever want to do that? If you choose R to always be non-negative, then you get to avoid those absolute values, which of course everybody would mark up as a win. Does that make sense? Yeah.
So just choose theta accordingly.
Do whatever you got to do with theta. Who cares? Theta is a non-issue. You can choose any theta values you want. Usually, obviously, you're going to pick whatever seems easiest at the time. Sometimes there's, alternative options that are sort of equally reasonable. But it doesn't matter is the point. Yeah. Right. Okay. So here's another example. Suppose I want to compute this integral on this domain, the domain being the unit disk here. And how would I do that? Well, again, in rectangular coordinates, square roots in the bounds, and it doesn't look good, right? I mean, maybe it works out okay. I guess we could try, but I'm not optimistic, right? So instead, we do it in polar coordinates, aka I'm going to pull back through the polar coordinates conversion formula function, except instead of drawing that, I'm just going to do all my slicing on the xy plane domain that I already have. So, as usual, dx dy is rd theta. as it always will be when you do polar coordinates as your change of variables function. So that's nice. And then my theta slices start here and then kind of go around like this, and I'm going to say they sort of go all the way around, if you will, and then end here. Now, do be careful of the slight sticky point here. It's tempting to look at this and say, oh, I'm starting and ending on the same slice. So doesn't this go from 0 to 0? But no, of course not. Keep in mind, this is just a convenience for drawing an actual pullback domain in which, of course, if this is theta equals 0, then that's got to be pi over 2, and that's got to be pi, and that's got to be 3 pi over 2, and you can see as we go around, theta has to be continually increasing, and so, of course, then this last slice, I need to pick 2 pi. So, my theta bounds 0 to 2 pi. Everybody see that? Now this, by the way, of course, happens a lot, right? That you go all the way around. Just remember, all the way around means theta goes from 0 to 2 pi. Okay. And then, now we arbitrarily pick a theta slice. On that theta slice, let's ask what the range of values of r is. Well, we're at the origin, that's where r equals 0. And we end on this point right here, which, keep in mind, this is the unit disk. That means the disk has radius 1. That means that at that point, r is 1. And so again, we're in business. What do you think? Everybody's all right with all that? Okay. Cool. Now, of course, then you gotta, don't forget to take your integrand. You have to kind of like collect your integrand. By the way, a common mistake is some students they'll have the r here, right, dutifully putting in their stretching factor of r, and then kind of just keep it hugging the differentials and then operate as if the integrand is just, this. Namely, just what came from the original integrand. And of course, that's not the point, right? The stretching factor becomes part of your new integrand. So you do indeed have to combine these together. R squared is your integrand, right? And then antiderivative, 1/3 r cubed and all that business. Okay. All right. So again, we're going to do a bunch more examples. A couple of tips and tricks. Pretty much always, I hesitate to say always, but pretty much always, dr d theta is the order to use. I can manufacture weird examples where d theta dr is actually preferred. They're pretty weird manufactured examples, though, and so I'm going to say this is hardly worth our time to deal with and to worry about. So just, practical purposes, just always do dr d theta. Okay. Here's the other thing. When you're writing down your differentials, keep in mind the point to these dr d theta differentials is that they are kind of what I'm turning my old dx dy integral into. Well, dx dy it's not just dr d theta. That's, again, the whole point, right? It is r dr d theta. That stretching factor's got to be in there. So, in fact, when you write down your polar differentials in the first place, always, please, always include r with the dr d theta as you write it down. Now, this is just advice. You don't have to do it. It's not, required. It's not mathematically essential what order you choose to think things through, right? But the phenomenon, and I've observed this over and over and over again, not just in students, even in myself here and there, right? Where I'm distracted, I'm thinking about the slicing and the ranges of values of the variables and drawing the picture, and it can be a little preoccupying, and then it's very easy to forget the R, to forget your stretching factor. The most important part of it, right? It's so easy to forget. So, nice little hack. Just always write r dr d theta all at once. Don't ever write down dr d theta by itself. Why would you do that? What's that got to do with anything? It's not a thing. It's r dr d theta is the thing. So I hope that makes sense. This is, again, a ritual, a life hack, math life hack of how to avoid the costly, inadvertent error of forgetting the R. Always write down the R with the drd theta. So again, hope you'll take advantage of that. And then again, look, we understand bounds from points that we identify as being on certain curves, which have certain equations, which we then solve. Okay, so all that's the same. So another example. Here we go. We have here an annulus. This is, it's kind of like a ring of some sort. I like to think of it as a moat. I don't know. That just appeals to my sense of humor, I guess. So this is a moat around like a castle or something. And that's our domain then for our integral. I'm going to do an integral of this expression right here. Maybe I'm computing the amount of water in the moat. I don't know. Whatever. How do I do this integral? Now, there is a strong temptation to say, So what I'm going to do is I'm going to compute the integral over the large disk, and then I'm going to subtract the integral over the small disk, and the big one minus the small one, wouldn't that then give me the moat that I'm looking for? Very temptation. Here's the problem. This integral over the entire disk, undefined. Because look at your integrand. Your integrand is basically 1 over r, and at the origin, that is not defined. And it's not a, what we call a removable singularity or removable discontinuity, right? There's actually a pretty massive explosion in the integrand happening. The function's approaching infinity. We have a nasty problem here of, the way we have defined things so far in this course. This integral here is not defined. So it could be, and y'all will probably remember from like Calc 2 classes, that there's this idea called an improper integral, and the thing is, it's weirder to make those ideas make sense in a multivariable setting. So we basically can't do that. So we're just dead in the water here. This approach of using the big disk minus the small disk doesn't work. Does everybody see why we have a nasty problem there? Okay, so we say, all right, well then let's slice and dice in the usual you might expect. Like I'll deal with that piece, and then this piece, and then this piece, and then this piece, and of course, who wants to do that? Now I have 4 separate integrals, each one of which has square roots in the bounds. Right? This is not attractive as an option. So let's call that plan B, right? Highly undesirable. So instead of either of those approaches, we're just going to do it in polar coordinates. And it's the easiest thing in the world in polar coordinates. My domain, again, this thing right here, let's talk about our theta slices. Well, we start at 0 and it goes all the way around to 2 pi. So 0 to 2 pi. That's our theta bounds. No problem. Then I draw and focus on a particular theta slice, like so, and ask now what's the range of values of r on that theta slice. And, well, let's see here. R starts at that point, which is on this curve, which has that equation, in which I can solve for R. Don't forget we're solving for R to find an R bound, and my lower R bound is 1. And then my upper bound is defined by this point, which is on this curve, which has this equation, in which again I can solve for, again I'm looking for R, on which R is clearly 2. So it's super easy to slice and dice in polar coordinates using, again, the appropriate polar slices. And with that noted, And remembering, you'll notice I glossed over this, but I remembered my stretching factor of R. Right? I wrote this down all at once so that I wouldn't forget the R. Right? And here's my integral. And combining the old integrand with the stretching factor, you see, in fact, my entire integrand becomes just 1. It's the world's easiest integral. My answer is 2 pi, and we're done. What do you think? Everybody happy with that? Sometimes polar coordinates is a massive win. Okay. Another example. Let's see here. Here we have a weird shape. You could think of this as like an eclipse or something if you want. Suppose this is my domain. Maybe I'm computing the amount of light coming off of the moon during an eclipse. I don't know. Something like that. How do we deal with this? Well, again, you could use rectangular coordinates. Nightmare. Corners. You're going to have 3 separate chunks, all of which are hard because their bounds have square roots in them. If you use rectangular coordinates, I think it's an easy pitch. We don't want to use rectangular coordinates. What we will do instead is think about theta slices. Now, one thing I want to warn y'all about. When you're drawing your theta slices, remember theta slices emanate out of the origin. There is a temptation to look at an annoying picture like this and draw your theta slices out of the center of the seemingly most important round thing in the picture. And that's just absolutely not true. So a lot of students will think of their theta slices as going like this. This is wildly wrong. This has got nothing to do with polar coordinates. Everybody see both the temptation and why it's wrong? Be very careful, please, not to step on that landmine. So that's all wrong. Okay, so with our center there, that's what a theta slice looks like. Fine. Where's the first and last? Well, the first one is over here at that point. Now, there's different ways that you can find the value of theta at that point. One thing you could do is take this curve, which has this equation. I'm going to say equation. This is, of course, an equal sign when you're on the boundary. So x squared plus y squared equals 1. Curve, equation, convert to polar coordinates. Right? Not that that's hard to do. Then once you have it in polar coordinates, then say, all right, but my point is also on this curve, which has this equation. Again, we're on the boundary, so equation. Convert that to polar coordinates. And then take our 2 separate equations. Oh, here was the first one. I already wrote that down. Take our 2 separate equations. And within those 2 equations, solve for, let's see, what am I doing here? I'm trying to find the value of theta. So I need to solve for theta, right? I'm looking for, I'm looking for the value of theta at this point. Looking for theta bound. So I need to solve for this theta in this purple pair of equations. Not that you can't do it, it's fine. But I want to point out there is a nice hack. Sometimes you get lucky. Sometimes there's little conveniences that'll make your life simpler. And I encourage you, when the opportunity presents, to please do capitalize on conveniences. So here's the clever move. That I shouldn't use green. That distance and that distance are both radii of that circle, which clearly has radius 1. So these distances here are both 1. Everybody cool with that? And then, but also this distance there is a radius of this circle, which has this equation over here, which again, radius clearly 1. So that distance is 1. And check it out, I now have a triangle here in which I know all of the sides are 1. Equilateral triangle, high school geometry, angles are instantly known. And so I can immediately infer then that this starting angle, keep in mind we're talking about this point right here, its value of theta, I can just see right here in the picture, negative pi over 3. Everybody see how we work that out from geometry? All right, so big. I think it's very nice to be on the lookout for these little clever opportunities. That's why I included this example, so you can see how that works sometimes. Yeah, sometimes you get lucky. Okay, likewise up here, another equilateral triangle up there. Same reasoning. This point then, pi over 3, positive pi over 3. Is everybody happy? Right. Okay, now with our theta bounds fixed, we're now going to set a value of theta. Start talking about r bounds. What can I say about the value of r? At our first r point is right there, which is on this curve, which has that equation. So, boom, r equals 1. And then our last value of r is going to come from that point, which is on that curve, which has, again, that equation. So, there's no way of getting around the fact that you are going to have to do a little bit of that algebra also, right? But then, again, solve for r, because we're looking for r bounds, and then r is that. So, we have our bounds, and we're in business. Right, all right? Okay. All right. Okay, so, now, but was it worth it? Here, was this a win? This integral is not just super, super duper convenient at a glance, but you know what? It's not that bad. This ends up being what we call a trig integral. And I know you all have seen a bazillion trig integrals back in your Calc 2 classes. And there's clever moves that you can do convenient things with trig identities when you have a bunch of trig in your integral. And the theta integral here works out. It's really not that bad. Whereas, again, the alternative, rectangular coordinates, 3 separate pieces, all of which would have square roots in the bounds, highly, highly less desirable than the polar. Okay. All right. This next one is a classic. This is, it's been around for a couple hundred years, I think it is, and it's a really brilliant move. Most mathematicians feel like, I wish I'd thought of this. I never would have thought of this in a million years. This is extreme clever. And it concerns this integral right here. Integral from negative infinity to infinity, e to the negative x squared. You may recall seeing this previously if you've ever taken a stat class, or if your Calc 2 class may have covered some stat in it. When you compute probabilities, you compute, depending on the situation, very often when you have a random variable, you're computing a probability, it's an integral of what we call a probability density function. And as it turns out, this is not only a probability density function, it's one of the most important probability density functions for very real reasons, very important reasons. It comes up in nature very commonly, and a lot to say about that. But anyway, this is an extremely natural integral to want to compute. Problem. This function does not have a convenient antiderivative. You may recall I talked about this in an earlier example, but you just can't write down the antiderivative of this function without using Taylor series. So we're in a pickle, right? So how am I going to compute this thing? Here's the move. Again, I wish I'd thought of this. I never would have thought of this in a million years on my own. But this integral, let's give it a name. Let's call it J. For seemingly mysterious reasons, let's compute J squared. Again, it's weird. I never would have thought of this, right? Who computes something by starting with the square of the thing they're interested in? It seems random. Here's J squared because there's J. And now this one looks a little bit different over here. I claim that, however, is also J. It's the same exact integral, just with a different dummy variable. So whatever. Just J times J. Now let's talk about this dy integral. That dy integral, I can take this value, and keep in mind, it's just a number. That integral right there is just a number. It's a value. It's a constant. Right? And I can again, counterintuitively, whip it inside of the dy integral. Legal. Not sure why I'd want to do that, but I guess you could. Right? And then, having done that, now let's look at what we have here. Notice we have an integral inside of an integral. Remember that means that for the purposes of the inside integral, the dx here, as I compute that dx integral, y is a constant, which means that e to the negative y squared is a constant, which means I can whip that inside of the dx integral. Everybody all right with that? It seems like I've taken an already hard question and I've done some extremely counterintuitive, legal, of course, but why would you? I've taken a hard problem and made it substantially harder, so it seems. Right? But check out what happens now. This, of course, just simplifies. That's a little bit of high school algebra. I can recognize all of this business here as just meaning that I'm doing an integral over all values of x and y. This is, in fact, then a double integral over the entire xy plane. Again, not clear why. How is this helping at all? We just seem to be making it worser and worser and worser until this move comes up. Let's do this integral in polar coordinates. And in polar coordinates, there's dx dy. Don't forget your r. Right? And let's see, what's the range of values of r and theta? Well, this is all possible values. Let theta go all the way around and let r go all the way out to infinity. This covers the entire plane, just as it's supposed to. And now when you look at this new inside integral, no problem, easy substitution. Thankfully, that stretching factor of r is exactly what we needed in order to allow a substitution to be possible. And so this is I'm going to call it an easy iterated integral. Perfectly doable. And it turns out that the value of this is pi. So keeping in mind that I was computing j squared, that means that j is the square root of pi. Isn't that cool? Again, it's out of nowhere, right? We have a problem that seems at a glance to be intractable. And by making it continually harder, step by step, I accidentally turned it into an easy question. So anyway, very, very cool calculation. Again, it's been around for a couple hundred years. Super slick move. All right. Okay, so we're going to go on to cylindrical coordinates now. And again, it's morally the same thing. It's a pullback through a coordinate conversion formula function. Again, when you're in cylindrical coordinates, here I am in r theta z space, and I can talk about, for example, theta slices, right? Slices perpendicular to the theta axis. They would look like this. But I can also ask, well, what would that look like in XYZ space? And, well, it would be kind of like that. This is what I like to think of as being it's kind of like a door where the hinges are on the z-axis. So what we would describe this, in this setting, we call this a half plane. And so I'm going to describe this as a half plane hinged on the z-axis. That's what theta slices look like in XYZ space. Same idea as we did in polar coordinates, just sort of one extra dimension. And likewise for the other slices. So, R slices just look like this, right? Constant value of R. And likewise, Z slices, exactly what you think they are. So, we can do all the same stuff then. Right? We can do a change of variables, aka a pullback. But we don't even have to draw the pullback. We can see everything we need to see in XYZ space, understanding what the slices look like. So here we go. A couple of tips before we proceed. You should always leave dr and d theta together and in that order. leaving you the only real flexibility that you need as whether DZ is on the outside or the inside. These are overwhelmingly your best choices of how to order your differentials. I really honestly, again, would not advise wasting your time with any other options. Think of this as your only two options that you'll ever need. Again, don't forget your stretching factor. So hard to uniformly, reliably, consistently remember it. It's so easy to accidentally forget. So again, my little life hack on making sure I will remember it is I don't ever write down drd theta dz without including r as part of that. So I encourage you to think of this as being a thing. After all, this is what dx dy dz is. R drd theta dz. Think of that as a thing. Don't ever write down the differentials without the stretching factor. And you're taking a big risk if you do. So anyway, don't say I didn't warn you. Then again, you need to pay attention to where the points are that define your bounds and identify them as being on certain surfaces. Look at the equations and then solve for what you want. That part, again, just like everything else we've ever done. So here we go. Let's start with this example right here. Upper half of a ball of radius A. There's our solid half ball. And I'm going to do this, by the way, two different ways. I'm going to start off with my dr d theta on the outside and dz on the inside. Yeah, just because. Whatever. We're going to do it the other way in just a sec. So, going through the process, theta bounds. Keep in mind, we have to remember what theta slices look like. And again, we've already talked about what theta slices look like. They're a half plane hinged on the z-axis. And so imagine, how do these theta slices go as you move all the way around the z-axis? And I think you can see they go all the way around. So, 0 to 2 pi. Is everybody happy with that? All right, so we fix the value of theta, and now let's think about on that theta slice, what's the range of values of r? Okay, the geometry, you got to think through. An r slice is a cylinder. This cylinder is what you get when you set r equal to a constant. So this is what r slices look like. What happens when I take a cylinder cross-section with a half plane, as drawn here? Or you might say, what is the intersection of this cylinder with that half plane? And, well, it's this line segment right here. And I think you can see that's always going to be what it looks like. So this right here is what an r slice looks like. Is everybody on board? R slice of our theta slice. Be clear. Okay. Alrighty. Okay. Well, so what can I say about my lower bound for R? Lower bound for R. The first R slice. Well, it's over here. Thank you. Picture, by the way. You got to have a good picture. So, what is the value of R there? Well, we're on the z-axis. That's where R is equal to 0. And then, what's our last value of R? Well, I knew that was going to happen. Last value of r is going to be, well, it's this real short little thing right there. And now we have to keep in mind what we know about this domain. This is a ball of radius a, which means that distance is a, which means in this case that means r equals a at that point. So convenient little bit there. Everybody happy with that? Okay, so then, again, we fix now a value of r in addition to having fixed our value of theta. So we are now confined not just to this theta slice, we are now further confined to this r slice of our theta slice, and we move on and now have to think about the bounds for z. Where does Z start? Where does Z end? Well, Z starts at that point, which is pretty clearly in the XY plane. And so we start with Z equals 0. And then, let's see, it ends at this point. And here's where you have to start being careful. That point, what do I know about that point? Well, it's on that surface. It's on the sphere, which has this equation in cylindrical coordinates. And again, we need it in cylindrical coordinates because we're studying this in cylindrical coordinates. There's the equation of a sphere in cylindrical coordinates. Now again, remind yourself what you're looking for. We're looking for Z bounds. So in this equation, I need to solve for Z. And that gives me that for my upper Z bound. How we doing? Cool. Don't forget, stretching factor, super easy to forget. Again, when you write down your differentials, you should always go ahead and put that stretching factor in as you're doing that, just as an insurance policy. Okay, so now let's do it the other order. Same exact domain, just doing it the other way around. So specifically then with dr d theta on the inside and dz then on the outside. So that's going to change all of the whole slicing process. Got to redo the whole thing. Starting with z, what's the range of values of z? Well, z slices, I think you can see, are kind of discs like this. Again, you got to have a picture. The picture tells all, right? And just, from the picture, if I have this solid ball and I take a horizontal slice through it, I get a disc. The first one is going to be right down there, where z is clearly 0. Thank you, picture. Gotta love the picture. The last one is going to be, well, it's going to be up here at the North Pole, if you will. And again, thank you, picture. The North Pole, the highest point on the ball, is on the z-axis. That's a geometric conclusion. I see that from the picture, from my understanding, my geometric intuition for balls. Right? And so that's going to be then also a radius, and that being a radius means that z is a. Is everybody on board? Okay. All right. So now we fix a value of z. So we're going to confine ourselves to this slice. And what then do theta slices look like? How does it look when a theta slice slices through that z slice? Again, geometric intuition. You got to look at the picture, and if we have a disc and a vertical plane cutting through it, and I appeal to your intuition that that slice is going to be a little line segment like that. On that line segment, where does theta start? Well, I mean, theta pretty much goes all the way around. Starts at 0, ends at 2 pi. So theta bounds 0 to 2 pi. All right. Now, fixing the theta slice, we move on to what do I know about r? Where does my r start? Well, I start at the origin. I start at the on the z-axis where r is 0. Right, and then I end at this point here, and again, here we are again. I got to figure out what I know about that point, and that point, well, it's on this surface, again the sphere, again with that same equation. Now, again, you see daylight, right, and it's tempting to run for the daylight, and it's just like it was in the last example, but keep in mind, here now, you got to be careful. We are solving for r, because we're looking for an r bound. So you solve for r in this equation, that gives you this different upper bound expression that is our r upper bound. Everybody all right? Is everybody following along? Okay. So, spherical coordinates. Same story, different pictures. Right? It's still a coordinate system that I can think of the conversion formulas as a change of variables function through which I can do pullbacks. The slices in rho phi theta space, I can push forward, visualize in XYZ space. I just have to think about what they look like. And, well, here you go. This is a constant value of theta, just like it was in cylindrical coordinates. They get a little weirder. This represents a constant... Oh, come on. How am I drawing? This represents a constant value of phi. That's weird. Our slice there is curved. Very strange. Well, you can imagine yourself taking a knife and maybe holding it at an angle and kind of working your way around or something. So that's not the worst thing in the world. Here, where it's just absolutely unrelatable, but constant values of rho are spheres. Right? And you can't do that with a knife. At least not with a straight knife. You'd have to have a bent. They probably have such a thing. But a bent knife, I suppose you could do that. But point being, this is, weird though it may be, this is what a rho slice looks like. So again, there's some tips and tricks that I think are advisable to pretty much always follow. The really good news, d rho, d phi, d theta should always go in this order. I have never in my experience naturally come across an example where this was not the best option. So again, I could manufacture all kinds of weird stuff, but I wouldn't see the point in that. This is just basically always the way to go. So always do your slicing in this order. Don't even bother with the others. And you're going to see one of the things that's nice about this is that it allows us to avoid a lot of the curves problems that we saw above. Again, don't forget the stretching factor. So important. It's the big multivariable calculus idea. If you forget it, it looks bad, right? What you've got written on the page just looks naive and wrong. It's wildly wrong and misguided. And I have to grade based on what's written on the page, right? So it's extremely important. Don't forget the stretching factor, and my hack for not forgetting the stretching factor, again, is to write it as part of this expression where I have the differentials and I write it down all at once. In my mind, I don't ever write down d rho, d phi, d theta alone, unless I just anyway, not on purpose anyway. Right? We all make mistakes, but I encourage you to think of this as one single thing: rho squared sine phi d rho d phi d theta. Right? Practice saying that fast. So you think of it as a single thing. You write it down all at once. It'll help. And of course, we're all mortal and fallible, but it will help. So, okay, example. All right. Suppose we have this ball here, centered up on the z-axis, radius a. So this you can think of this as kind of sitting on top of the xy plane at the origin. Okay. Alrighty. Following the advice up here, we're doing our theta slicing first. Right? Always outside in. So theta slicing first. Theta slices look like this. I think it's a fairly easy pitch that this goes, that this goes all the way around. And so 0 to 2 pi. Ready, buy it? Okay. Then we fix the value of theta. So we're going to be looking at this theta slice. For that value of theta, and I'm going to gripe about the where we're at now, looking at that picture, and frankly I find it a little hard to see what's going on in that picture. We're looking at that picture. This is a nice flat half plane, but we're looking at it at an angle, right? And it's just a little confusing. So what I like to do, you don't have to do this. I find this to be helpful, though. I like to just go ahead and redraw that theta slice in such a way that you're looking at it edge on, or straight on. And I just find this to be easier to look at. I don't know. Everybody's different. If you don't want to, you don't have to. But I think this does make it easier. I think this will cut down on geometric mistakes, misinterpretations, because you were looking at a hard picture. Up to you, your consideration. Okay, so now let's talk through the phi slices. Now, keep in mind, let me come up here for a second. Here's our theta slice. A phi slice, we talked about before. A phi slice is a cone. Oh, come on, man. There we go. It's a cone. So we have to think now, what does it look like when a cone intersects a half plane? And, well, appeal to your intuition, that intersection is just a kind of a ray coming out of the origin. Right? Does that make sense to everybody? You just got to see it from the picture. So in my new freshly drawn theta slice picture, rays coming out of the origin are what my phi slices look like. And so I just want to think about starting and ending values of these phi slices, these phi rays that are coming out of the origin. Now, here we are again with the same danger, and again, I get the sort of the how easy it is to make this mistake, but if you look, again, my laptop, I'm sorry. If I look at my theta slice, it is tempting to think of, so phi is stuff like this. These are phi slices. Doesn't that look tempting? And it's tempting to say, so 0 to pi. That's not phi. Phi does not come out of the center of whatever seems to be the most prominent round thing in your picture. And I know that everybody knows that. But as you're working, it's easy to accidentally just kind of go a little bit too quickly and oops it. Comes up a lot. I see this a lot on students' papers. So heads up, please don't let that be you. Don't misinterpret your phi. Phi slices come out of the origin. And so my first phi slice is 0. And my last phi slice, as I, kind of go along here, where you sort of run out is pi over 2. And you could try to convince yourself of this by perhaps entertaining, any value of phi greater than pi over 2 would be heading down. And there isn't any slice down, it's all up. What do you think? Everybody happy with the pi over 2 claim? Okay. So fine. So now we're looking at our phi slice of our theta slice, and we play the continuing game of now. Oh, by the way, let's go ahead and document. Theta went from 0 to 2 pi. We just argued that phi goes from 0 to pi over 2. Again, easy to mess that up. It's pi over 2, not pi. And with all of that settled, now we're going to move on and think about rho. What's our range of values of rho? Well, rho starts at the origin, where rho is 0. So no sweat. And then it ends at this point, and again, here's where I got to actually do some work. That point is on this curve. Wait a second, where'd that curve come from? That curve, aka this curve, up here in my original picture, it's that curve. It is, in fact, part of the sphere. Right? And keep in mind, what we drew down here was just kind of a geometric, kind of an artistic convenience. right? But in actuality, we're slicing up on this three-dimensional solid in this three-dimensional picture, and so that outer bound point is on the sphere. So you've got to play the game of, you've got to take the rectangular equation for that, convert it to spherical coordinates, and then in this equation solve for rho. Oh good, it's already solved for. And so there's our upper row bound. Everybody happy? Don't forget your stretching factor. Again, so easy and so tragic. Don't forget, please, 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 right? Nobody, myself included, nobody wants you to forget that rho squared sine phi. So write this down all at once. Y'all have a nice day. See you on Friday. All right.
Did you stay on this page?
I'm sorry?
Did you stay on this page?